This presentation is a part of my coursework under Dr. Basant Namdev sir. We will explore how computers efficiently draw circles on a pixelated screen. Moving on to the next slide. Challenges and symmetry. Let's start with the challenge. Drawing a circle seems simple to us, but for a computer, calculating points for a full 360 degrees is incredibly slow and redundant. However, circles have a special property called symmetry. If you look at the diagram, you will see we don't actually need to calculate the whole circle, we only need to calculate one small slice, specifically the first octant from 0 to 45 degree. Once we find a point x comma y in this section, we can automatically determine the other 7 points just by swapping coordinates and signs. The key takeaway here is efficiency. By doing this, we reduce the computer's computational load by 87%. Moving on to the next slide, which is midpoint circle drawing algorithm. So, exactly is the algorithm? In simple terms, a circle drawing algorithm is a method used to decide which specific square pixels on a grid, like your monitor, should be lit up to look like a smooth curve. The midpoint circle algorithm is a specific, highly efficient technique for this. Its main superpower is that it uses only integer arithmetic. It, avoid, it avoids heavy floating point math, making it extremely fast and rasterization. Moving on to the next slide. Midpoint strategy. Now, let's look at the strategy. Imagine the computer has just plotted a pixel and needs to move to the next one. As the circle curves the algorithm has to make a choice between two pixels. First, the east pixel, which is E, which is directly to the right, having coordinates x plus 1 comma y, and the other southeast pixel, which is diagonally down, having points x plus 1 comma y minus 1. How does how does it decide? It looks at the midpoint m exactly halfway between them. The logic is simple. If the midpoint is inside the circle, the true curve is higher, so we pick the east pixel. If the midpoint is outside the curve is lower, so we pick the southeast pixel. Moving on to the next slide, which is the decision parameter. To make the decision mathematically, we use something called decision parameter, which is denoted by p of k. This value comes from the circle equation, which is x square plus y square minus r square. It acts like a test to tell us where that midpoint lies relative to the boundary. Here are the rules we follow. First, if p of k is negative, which is less than 0, it means the midpoint is inside, so we choose pixel E. If p of k is positive, which is greater than or equal to 0, it means the midpoint is outside, so we choose pixel SE. This simple sign check tells the computer exactly which way to go. Moving on to the next slide, which is recursive optimization. Now, if we calculate that full equation every single time, it will be slow. So if we use recursive optimization instead of calculating squares from scratch at every step, we use the current value to find the next value using simple addition. We start with an initial value of 1 minus r. From there, we just update it. If we choose east, we add 2x plus 1 to our parameter. If we choose southeast, we add 2x plus 1 and subtract 2y. This turns a complex geometry problem into simple addition. Moving on to the next slide, which is algorithm workflow. Let's put it all together into the workflow. Step 1. We set our radius r, start at point 0, r, and calculates our first decision parameter, which is p equal to 1 minus r. Step 2. We enter a loop. We keep going as long as our x value is less than or equal to our y value. Step 3. Inside the loop, we plot the point x, y and all 7 of its reflections. Step 4. We increase x, then we check p. If it is negative, y stays the same. If it is positive, we decrease y. Then we update p using the formulas we just saw. Moving on to the next slide, which is numerical trees. To prove this works, let's trace it with an example where the radius is 10. We start at 0, 10 with a p-value of minus 9. Step 1. P is negative, which is minus 9. This means we are inside, so we choose east. Our point point is 1, comma 10, we update p to minus 6. Step 2. P is still negative, which is minus 6. We choose east again. Point becomes 2, comma 10, p becomes minus 1. Step 3. P is still negative, minus 1. East again. Point is 3, comma 10, p becomes 6. Step 4. Now p is positive, which is 6. This means we are outside. So we must drop down to southeast. This point becomes 4, comma 9 and p updates to minus 3. You can see how the algorithm hugs the circle boundary. Moving on to the next slide, which is summary and advantage. In summary, the midpoint algorithm is an industry standard for a reason. Its advantages are clear. First, integer math. It avoids floating point errors and overhead. Second, efficiency. It uses only simple addition and subtraction inside the loop, no multiplication or division. Third, accuracy. It generates the closest possible approximation to a true circle on a pixel grid. That concludes my explanation of the midpoint circle drawing algorithm. Thank you for your attention.